let's go over this bonding chapter. And again, this is going to set the stage for what we're going to be doing in the next few weeks. And it's still building on what we were just talking about in terms of the atom, right? So one thing to think about when we're talking about chemical bonds is that these bonds that can form in many different ways, but they're guided by those electrons that are found in those shells, all right? So the outer shells that we were talking about in the previous chapter, all right? And the arrangement of those of the bonds that you have is going to confer different properties on the molecules that are being examined, all right? So for example, I mean, I love looking at carbon because it is very versatile in the way it will bond. It can bond to itself. It can bond to other types of atoms. And it's very promiscuous in that it can do so in many different ways, as well as, like I said, with many different atoms. And that's partially to do with the fact that largely to do with the fact that it has 4 valence electrons. So it's neither wanting to give up or take. It just wants to get to its octet. So it's very versatile. So you can see here, carbon can exist as soot, right? High temperature and pressure, you can get diamond. And the different types of bonding, you can see these beautiful types of structures. You can have sheets like in graphite. So anyways, you see what I'm saying here. So let's move forward and talk about how this is working, all right? So the driving factor, and the simplest way to look at it, there's always some exceptions in nature, but the simplest way to consider this is that atoms are trying to get to stability, right? They want to be the most stable they can be. And in so doing, in order to be stable, they have a full set of electrons in its outermost shell. And most of the time when we're thinking about this in terms of learning, we talk about the octet rule. So having that full shell of electrons in the outermost valence shell. So when you look at this, and it sort of drives their types of chemistry. So if you look here at the noble gases, that's what this column here is called. And these are very unreactive. Okay, these are gases that exist as they are, and like I said, they don't react, and they have a full 8, all right? Whereas if you look at the halogens, which is right next to it, they have 7 valence electrons, right? So they would like to take one more electron, and they'd be able then to have a full shell. So if they have a full shell, or 8, they're inert, right? So the inert meaning that they don't react with anything. On the other side, if you have 1 electron in the outermost shell, which is what you're talking about here with these alkali metals, they are also very reactive in the fact that they would just like to lose that electron that they have, and then they'd have a full shell. They'd be the next row down, so this would be down here, okay? So go figure that the halogens and the alkali metals react very well with each other because one wants 1 electron and one's willing to get rid of 1, all right? So you can sort of see how this desire to get to a full 8 is very indicative of their chemistry, all right? So one way to really think about this is by looking at sodium and chlorine. And I've got to just see if I have the periodic table here. Nope, but anyways. So if you remember the periodic table in the room, right? So sodium just has 1 valence electron, and it's sitting out here, and chlorine has needs 1. So you can see here's the chlorine is needing 1, and here this one is willing to give 1 up, right? So here's its outermost shell, as you can see. And the interesting thing to remember here is that sodium and chlorine, when they are in their elemental form, they have very different properties from each other. But when they come together and they form sodium chloride, which is table salt, so you should probably recognize that. So table salt is just salt. I mean sodium chloride, I should say. it has a very new property. So when you combine these two elements together, you get a compound with different properties. So what we say now, so if sodium now loses its one electron, all right, it is going to look like neon, because neon will be in the row above, and that is your noble gas on that side. But it's not neon because it has a positive one charge. All right, so here's your sodium ion, and it's positively charged. All right, so we say it's a cation. So later on when we do batteries, remember cations are going to go to the cathode. And before, when I was talking about the electrochemical cell, originally in chapter 3, I think it's like the second slide, I said that the anions are going to be going to the anode. So the anions are the negative ions. So here's your chloride, all right? So if you look at the next neighboring, so that the halogen next to chlorine, so now it's gained that electron as a full 8, it is now, a noble gas, not halogen, it is a halogen. It takes on that noble gas. It is now going to look very much like argon, but it doesn't have the same behavior as argon because it has a -1 charge, all right? So when we make an ion and we make it look like something else in a way, we say it's isoelectronic with that other element, all right? So chlorine is now isoelectronic with argon, but it's not argon, all right? It has a negative charge. Argon does not have a negative charge. And sodium is isoelectronic with neon, but it's not neon because neon does not have a positive charge, but sodium ion does, okay? All right. Now, again, remember what we're trying to do here is form that octet rule. So chemical reactions can take place either to gain or lose or share electrons so that you have that full valence shell. Now, the only exception that we're going to have in this course is that first row. So remember, the first row is just an s orbital. There's only 2 electrons there, so hydrogen and helium, they don't have a full 8. They want to have 2. So that's what the desire is there. So hydrogen would like to gain one, would like to give up that electron, so essentially, is naked. But you can see that it's going to be very reactive then with chlorine, which of course wants 1 electron, and you get hydrochloric acid. All right. So when we look at this, our metals, so let's go over here, go back to this little thing. So we've got our metals, all right, they tend to want to lose electrons, all right, whereas on this side, halogens, all right, so our nonmetals, or on this side, they tend to want to take on electrons, all right? So if we look at this here, so here, metals will lose electrons to take on the electron structure of the previous noble gas, all right? And in so doing, they form positive ions or cations. And nonmetals tend to want to gain electrons and take on the electron structure of the next noble gas, right? And so doing, they become negative or anions, right? Okay. So if you look at this, and you can see that you can almost predict a lot of the charges that the metals and nonmetals will have, all right? Now, when you look back here, though, okay, there's going to be these ones here. These are our Ds, if you think back to the last chapter. These guys are transition, so they're going to become more metallic as we go across here. And it's so some of these, what we call transition metals, and some even a little bit over here, they have a possibility of having more than one type of charge, all right? So if we look over here, for example, and we look at these different charges, you can see down here that you have iron. It could be a +2 or a +3, okay? Or copper, it can be +1 or +2, all right? So some of them, there's a bit of flexibility, and that happens because the outermost shell is a D, and that, remember that some of those Ds, if you look at the filling of them, can be surrounded by S's, all right? If we go back, remember we're talking about filling these orbitals in order. So they have a bit of flexibility in that region, all right? But still suffice to say, they have certain numbers. There's a limitless different types of combinations. They're usually 2, sometimes 3 different possibilities, all right? Okay, and you can see that they're named as such, all right? I'm just looking at my notes here to make sure I'm not forgetting to say anything in my video. Okay, oh, and I forgot to tell you, this one here, we call this an ionic bond because it's between two different ions, right? That's in my notes for these slides, but I'm gonna talk about them anyways. So we're gonna move forward here. Okay, so here, you can see that, like I said, there's going to be some with more than one possibility of charge. So remember, cations, the charge of the cation for those representative elements is typically the family number, all right? So obviously the transition metals are a little bit different, but it's typically going to be the charge, the same as the family number. So sodium ion would have a positive charge, and magnesium could have 2, all right, because it's in the second column, all right? So how do we get the name of that positively charged ion or cation? It's simply the name of the element, so the sodium ion or magnesium ion. Now, when we're talking about the negative charges, the anions, all right, so the charge of the anion is representative, or is taken from the family number -8, so then you're going to get a negative, right? You can see that then you can have -2 for oxygen and -1 for chloride. Now, how do we name this? Well, I just said it. Sorry, can't help myself. But the name of the anion then is the root of that element with an "ide" after it. So instead of saying chlorine, because now we have an ion, we say we have a chloride ion, and oxygen is an oxide ion, all right? And then when you name them together, so the beginning part is just the name of the element anyways, or the ion anyways, so sodium with its chloride, or magnesium with the oxide, all right? So that's to just sort of orient yourself with these names when we're going through here, okay? Now, remember then that these ions are going to drive the chemistry, right? So here so remember that some of these transition metals have more than one possible charge, all right, just because of the nature of their structures. And then the Roman numerals here will tell you. So you might see this in your homework. So if you see this 2 here, they typically tend to be positive, all right? So you see this, you know, it's going to be iron with a 2+, or a 3+, or copper with a 2+, or a 1+, all right? So as we go through. But other ones will not have that, so silver is always just the 1+. As we go, all right? Okay, now, types of bonds. So saying that the chemistry is really dependent on the electrons, and specifically those electrons in the outermost shell. And I'm going to open with a type of bond called the ionic bond, because we were just looking at ions, all right? So here, when you've got an ionic bond, you have 2 ions, opposite charges, and they're coming together. And it's actually quite a strong bond, a weak bond. And if you think about it, you know it's weak. If you put salt in water, it comes apart, all right? But what's happening here is that the electrons, we're not sharing them, all right? And you have an attraction, sort of an electrostatic attraction between these opposite charges. And very often, these ionic compounds can form crystals, right? So you're used to seeing this one. We always use salt as the example, because that's usually the one that you can relate to. And indeed, crystal lattice of salt has these beautiful cubes. If I remember it, I'm going to bring in some salts of some other things that I have actually in my house. I'm weird that way. Okay. Now, another type of situation, remember I said you could share, give or take electrons. So the next idea is sharing of electrons. So here, if we look again at our ionic bonds before we get there, so we have our sodium and our chloride. Remember, this is going to be a weak bond. It's an attractive force between opposite charged ions. The positively charged cation is going to form with a negatively charged anion, right? So here we can see we have a nice stable shell on the outside, right? So notice that now the valence shell is stable on both of them, even though they have now become isoelectronic with the certain noble gas, right? So sodium neon and chloride argon, all right? Now, covalent bonds. So here we have a situation where we are sharing our electrons. So there isn't a situation where the elements are so different that they're ripping or taking away an electron or giving it away, all right? So here we're sharing them, especially when we're talking about covalent bonds. These are very strong bonds, okay? not easily broken, and there's a lot of energy stored in them. Now, we can have different types of covalent bonds. We can have single, double, or triple bonds between these, depending on how the atoms are sharing those electrons, all right? So when we're talking about sharing, we can share them in different ways. We can have polar and nonpolar, and I'm going to talk about that, all right? So now, if you have a situation where you have a sharing, so like, a hydrogen molecule, usually the way this is done classically is that you can say how many of each of those elements are in the structure, all right? So if you're looking at a covalent compound that has the first part, you have the first one, so you say like mono, di, or tri, or however number of that element you have, and then the second part, again, you'll say how many of the second ion you have, all right? And the second one, you're going to end with "ide," right? So here, this would be sulfur. You need to say this first one. So sulfur, tetrabromide, or so 4 bromines, diphosphorus trioxide is how that's named. And usually, and I'm going to talk about this again, the more electronegative is going to be the second one listed. So the one that's further to the right on the periodic table is typically the one that's labeled as the "ide." And very often, though, as you can see, we will drop the mono, all right? So if there isn't a prefix, it's just decided. So you're not saying monosulfur tetrabromide in this case, all right? So it's sulfur tetrabromide, all right? So that's how we would name these when you see them, okay? So here we have this sharing of electrons and the electronegativity, or how electronegative or how negative these elements are, is going to determine how these are going to be shared, right? So what is electronegativity again? So that's a measurement of how much an electron is going to want to hold on to electrons, all right? So the attraction of an electron in the bond. And this was an idea that was coined by Linus Pauling, and he is the one that actually assigned electronegativities. And if you look back at the trends across the periodic table, you could see from chapter 3, you can see that I have arrows going from the left to the right in terms of how electronegative these things are. Now think about it. Now this is going to be wanting to attract electrons. And if we think again about our halogens, they want to attract electrons so badly that they'll just take it from one of our metals, right? So clearly these guys, these are bigger, there's more electrons, they're more negative, so they're going to be more electronegative, right? So they're bigger guys, and they're going to be, so you can sort of think of them as more like bullies, and they're going to be sort of dominating the reaction, all right? So the more electronegative, the more the atom will want to attract those electrons, okay? All right, now, so with this, we can have electrons shared nicely, right, equally, and we can have electrons shared unequally, all right? So if they're shared nicely or equally, we say we have a nonpolar covalent bond, all right? So this is classically between two atoms of the same element, so H2, O2, etc. All right? So here you can see that both of these hydrogen molecules, atoms, would like to have one more electron, and they'll play nicely in the sandbox, and you'll get an H2, and you can see that both of those atoms are very happy. And it's nonpolar because it's basically the same all over this molecule, all right? Now, the next idea clearly is going to be a polar covalent bond. In this case, we're still sharing, but we're not sharing these guys equally, all right? So this is coming back to, I would shown you hydrochloric acid before, all right? So you know that hydrogen, being in the first row, clearly has fewer electrons than chlorine, which is in the next row. So it is definitely the stronger pull, all right? And here we're not sharing these guys equally, all right? So there's a sidedness to this, all right? Now, so one side is going to be more positive and the other side a little bit more negative due to the difference of their electronegativities, okay? Okay, so if we look at this, this gives sort of a polarity to the bond that we have. And the side that is got fewer electrons So therefore, the electrons are going to be more heavily favored towards the chloride, all right? In this case, we say that it is more positive on this side than it is on the other side, okay? So we say slightly. This thing has a delta sign. As a chemist, right away, I think slightly positive, and on the other side, slightly negative, even though it is a delta sign, okay? So technically it means partially positive or partially negative, but not full on because it's not an ionic bond, it's a covalent bond, all right? Okay, but overall, this molecule is neutral, all right? Because these things essentially cancel themselves out. But if you look at the distribution of electrons over the molecule, you can see that one side is more negative and the other side is more positive, and that's going to affect its molecular chemistry, all right? Okay. So now when we have these polar molecules, all right, or these situations where we have an unequal sharing of electrons, we have these things called polar molecules, because the molecule over the whole thing has a polarity, all right? So water is a classic example, and water has so many interesting properties because of its structure and its polarity, all right? And very often we can think of water as behaving like almost like a magnet. So there's a positive side of the magnet and a negative side of the magnet, all right? And this comes to the idea of the next type of bond, which we call a hydrogen bond, okay? So a hydrogen bond, all right, I think that's it. Okay, let me finish this about water. So water is a really good solvent because overall it is polar. All right, so this side that is slightly negative can react really well with something positive, and on this side, it can react really well with something negative. So if you look at a salt, for example, so water is an excellent solvent. Solvent is the liquid or the medium in which something else is dissolved in, and the solute is the thing that's dissolved, right? So solvent, that's doing the dissolving, and the solute is dissolved. Now, if you look at, say, our sodium chloride, our ionic molecule, right, which forms a beautiful crystal when it's a solid, but wow, when it's in water, it just comes apart. And the reason it does is because those water molecules, the positive side where the hydrogen is going to orient itself along those chlorides and pull them apart. And on the other side, this positive sodium ions are going to be surrounded by the slightly negative side, or where the oxygen is in the water molecule, and sort of pull that whole thing apart. Okay? Now, hydrogen bonds. So now we're talking about a molecular bond. It's something that occurs between molecules, not between atoms. Okay? So we're talking about these molecules that have this polarity, and they can now form this hydrogen bonding between each other, right? So say between different water molecules, or in this case, as you can see, a water molecule and an ammonia molecule. So you can see ammonia is also polar, right? Notice you probably notice that very often these polar molecules involve hydrogen, and indeed, very often we say that these bonds are between the hydrogen and the electronegative bond, and that would be our hydrogen bond. So if you look at my notes, typically, and it's very often in biology, you see it between nitrogen, sulfur, and oxygen with a hydrogen, or over a hydrogen, all right? So you see this kind of thing. So if you have an NH, you've got another H over here, and it will form, this is the actual hydrogen bond of this polar molecule, where we have these polar covalent bonds, okay? So these are happening between these polar molecules, all right? And then I showed you this kind of an interesting video here where we could see the conduction of charge in different solutions and what happens with water, all right? But like I said, we'll understand this a little bit better when we go into chapter 6, okay? Okay. Now, there's one other type of bond, and we're going to talk a little bit more about this later because it's kind of a weird bond, but it really comes down to the fact, if you remember that those electrons are not just sitting in one space around each atom. Remember, they are in harmonics. They are in a wave form around each of those atoms. And if you look over the entire spectrum of a molecule, all right, this fact that these electrons are moving can induce hot spots of positive or negative charge distribution over a molecule, all right? I know that sounds weird, but suffice to say it is a thing, all right? So this creates sort of a weak bond that for now we'll refer to as a vanderwaal's bond, because you've probably heard of this before. We don't even have a bond, it's like an attraction. And again, it's going to be between molecules. It's not between different atoms, this is between molecules. So hydrogen bonding and van der Waals is between molecules, whereas ionic and polar, that's between the atoms themselves, okay? So now one good example would be how a gecko seems to just crawl up a wall, right? The first time you see that is kind of cool. Like, you've seen pictures of it. When you see it in real life, it's really interesting. The first time I saw that was when I was in India. So, you know, there's geckos all over the walls there. But the way that they're doing this is that they have proteins or molecules on these little hairs on their toes that can interact using van der Waals interactions with the wall or the surface that they're crawling over. And we're trying to do this, especially in terms of robotics, so that robots can hold on to very nicely onto substances or glasses like bowls and things like this. So you imagine robots, and they need to be able to hold on to things, and because they don't have muscular structure, and you don't want to have too much pressure because that causes breakage. So the idea is to try and use van der Waals, and here you can see an example of this. Okay. All right, now, so here's another example that you would actually might be able to relate to in terms of van der Waals, is how different types of drugs might interact with their receptors. Those are not covalent bonds. These are a mixture of van der Waals and ionics, and of H bonding. But overall, you can see that overall these molecules can allow for this type of bonding. And drugs actually tend to mimic natural types of interactions, right? So here, morphine and your endorphin. So, you know, if you're a runner, you have, you know, that thing called the runner's high. So it's sort of the same kind of idea. It binds to the same receptor, so endorphin receptors, okay? All right. Now, how do we represent these? Now, this is going back to some classical chemistry, all right? But it's helpful to understand how these work so that you can have a greater appreciation of what's happening at a molecular level, all right? So polyatomic molecules is when you have, you know, two atoms joined by covalent bond over overall electrical neutral, and now we're fulfilling this octet rule, all right? These molecules are going to be functioning as a group, okay? So like we were just looking at water and ammonia, another one would be methane. And, you know, overall, the octet rules have been satisfied between the atoms, and now we have this molecule. Now, some of these polyatomic molecules can have a charge, right? So then we say that they are polyatomic ions, and here you can see some. So here you have ammonium and hydronium, and you can see that there's more than one element in here, and overall they have a certain structure and they have a charge, and they function now, instead of a single atom in an ion, they function as a molecule with a charge, all right? And they have their own sort of chemistry. So when you're writing the formulas for these, all right, you can sort of see how it's done. So here you have your positive, so this is your ion, or your positively charged cation binding to the anion. And you name it similar to how we named it before. You have your first one just being calcium. But now you're going to have an 8 here. So nitrate, all right? So, and some of these can have more than one charge, as you know, we'll see. Sometimes you'll see it nitrite. And that's because the molecule is slightly different, all right? And that will sort of designate how we know them apart, all right? But if you're seeing something like this, and then if you see these brackets, all right, or parentheses around a molecule, you can see that you right away know that this is going to be a polyatomic ion, and here it's going to tell you how many of those you have, right? So if you look at calcium periodic table, likes to be plus 2, And nitrate has a -1 charge. So in order to balance this out, you're going to have 2 nitrates bonding with 1 calcium, so calcium nitrate. Okay, now that can work the other way. So ammonium, as you can see, is positive, and it can bond with another polyatomic ion, so sulfate. So in this case, you have ammonium and sulfate. So here you keep the one that's positive, you still keep the root, the name of it, just as we did before, okay? But here you can see we're ending it with 8 instead of ic, as we did before, or ide, I should say. Sorry, ide. All right? Okay. Now, in chemistry, you'll see that a lot of these things are drawn with dots. And this is just to sort of tell you what's happening to those valence electrons. And these valence electrons are just drawn as dots, all right? And remember, typically we can have up to 8. So if you look at our noble gases, you can see that we're drawing them in pairs. And remember, it makes sense because when we're filling up the orbitals, remember you can have 2 electrons in each orbital, spins are opposite. And you can see that this is how this is working. So then here you've got 1, here you've got 2 open, you've got 3 open, and so on. All right, carbon, there's 1 on each side. Right, so, and then you can see here where there's only 2, right, we're drawing them on opposite sides. So it's telling you where these electrons are, in a sense. All right, and then you can sort of see the reactivity. All right, so these valence electrons then are drawn as dots. Okay. Now, if we join them, we can keep these electrons. So here we have water, right? So we have 1 electron, and here's the 2 free, and they'll come and bond together. And if you look at the oxygen, it looks like it has a full 8, and the hydrogen now has its 2, and it's very happy, right? The same thing when we're dealing with ammonia, all right? And as well here, this is methane, all right? So what you're going to do is you're going to count your valence electrons, so you can sort of sketch it out. And you place those electrons as pairs, and eventually, so you can get rid of the electrons used so far from the valence number of electrons until you have them all filled up. Okay. Very often, you think of the central one, not having an octet because it's sharing, in a way. But you basically just fill this in. All right. And if it doesn't quite work, that means you probably have a double or triple bond. All right. So, and then you can sort of plan accordingly. And the only way to sort of get used to this is to do some. I'm not going to stress that a lot here in this course, but it's important that you're familiar with it. All right. Okay. Now, this will also give some information to the shape of the molecule. So I just we'll get there. All right. So the other thing that I want you to notice is that you can take the pairs and you can just draw them as a line. That makes it a little easier to look at. Right. Which is sort of what's done here. Instead of showing all those little dots, it's just drawn as lines. Now, they also have these things, the ball and stick models, so you can sort of see this. And notice that we're starting to get some shape here, all right? And I'm going to explain how we get this shape. And that's referred to as the valence shell electron pair repulsion theory, VSEPR. So VSEPR, what this is all about, now remember, electrons are negatively charged. And if you take the 2 negative poles on a magnet and you pull them them towards each other, what happens? Well, they repel each other, right? So they're going to want to repel each other. So that is also what's happening within the molecule. So when you've got these pairs of electrons and these bonds, the electrons are going to distribute themselves in 3 dimensions. And it's an important thing to try and imagine it in 3 dimensions so that not only, so that they don't interfere with each other. Because remember, these things are negatively charged and they're also acting as waves, right? So what ends up happening is that the molecule will skew itself into a shape so that these electrons are as far apart from each other as they possibly can be. And then we sort of name the molecule as such, okay? So if you have the repulsion so that it forms lines, it's called linear. Here we're talking about a triangular shape, all right, so trigonal planar. And tetrahedral now is when you've got sort of a pyramid, all right? And keep in mind, this space here might be 2 electrons, all right? So if you have a situation, so I'm trying to think of, so if it was, trying trying to think, I can't think of one off the top of my head right now. But sometimes there would be an electron pair on each side, or and that would, in case you could also get something that's called bent. All right. So, but the main ones would be linear, trigonal, planar, or tetrahedral. Okay. Now, if we look at it here, you can see most of the shapes. So here you've got linear. Here's your trigonal planar. Here's your tetrahedral. All right. And then you can get to this thing called trigonal bipyramid. We're never going to see these, but what I want you to, in this shape, but in this course, but what I want you to see here is that, so if you have tetrahedral, you've got 4 different atoms around a central atom. But remember, I had said to you that you will, if you can't form a bond here, you actually have a lone pair of electrons that can go into the shape as well, because they will repel these other 3 bonds. So if you have a situation where you have 3 bonds and a lone pair, the structure is also actually called trigonal pyramid. And this is what I was just saying. Here you've got 2 elements bound to a central one, but if you have 2 lone pairs, those lone pairs, those clouds of electrons, are going to be pushing this out. So you won't get linear, but you'll get bent, okay? And the same thing as we move forward here, right? So here you can have octahedral, where you have 6, and then again, as you switch these 2 lone pairs, you're going to have these different types of shapes, okay? And what I want you to see here you've got 4 lone pairs and 2 different atoms, and again, you've got linear, right? So you have linear here when you don't have lone pairs, but here you've got linear and you've got 4 lone pairs, all right? So you can have slightly different shapes, remembering that you've got these positioning of these electrons, right? So lone pairs can actually behave as if there was a bond there, okay? So that's sort of what I'd like you to think about when you're contemplating the shape of these molecules. Now the last thing, oh yeah, and here you can see some more drawings of this. So the interesting thing is that, again, there's going to be one that's more electronegative. So here again, we're going to have these polar and nonpolar molecules. So remember, the positive, the more electronegative, all right, it's going to be creating an unequal distribution of the charge. Now, at the bond level, something like methane overall could be balanced, but nitrogen, on the other hand, won't, because it has 5 valence electrons, 3 of them are forming bonds. Here you've got a lone pair. Oxygen, there's 2 lone pairs, right? So here's your bent, right? I can't really remember what this one's called. Where's my one lone pair? Here it is, trigonal pyramid. That's the one that was in my head, but I wanted to check. So you've got your trigonal pyramid, all right? So here's your lone pair, all right? So that will have an overall effect. Now, sometimes there are these cases where you have odd electron numbers, and these guys are special molecules. They're called free radicals, and you might have heard of them before, but they have some really interesting chemistry, right? They have this desire to get a pair. So they love to take electrons away from something else, almost like an ion, but these are really damaging. They will literally strip electrons off of other molecules. And we'll talk about later on, we call them as oxidizers, all right? They're going to oxidize by stealing electrons, right? So another way of thinking of them as scavenging. They're going to scavenge electrons from anywhere they can, and they can be very, very damaging to the body. And we can create them in the body by exposure to chemicals and toxins, as well as sunlight. And you'll probably have heard of antioxidants, taken some antioxidants, things like beets have lots of antioxidants, blueberries, lots of antioxidants, pomegranates. And the reason they say you should have these in your diet is to try and scavenge or to try and neutralize these free radicals. All right. So here you can see we're going to talk about some of these gases later on in the semester. So NO, NO2, and ClO2. So these are very often found in the atmosphere during pollution. Okay. So you can see why they're toxic. All right. So these free radicals are very unstable. They can damage tissues. And again, like I said, we can use antioxidants to try and neutralize these. But they also have some very powerful chemistry. All right. So here again is another idea here. So antioxidants are going to sort of stop these guys. So I'm trying to find good examples. So here's the antioxidant, which will allow for, give an electron here. Now, I had some students working on these in my nutrition class, sort of talking about these as a topic, like you guys have your hot topics. But I did this in a nutrition class, and they brought up the idea that, well, then, doesn't the antioxidant become an oxidizer because it's now a free radical? So, and there is an element of that, okay? But suffice to say, some of these are more reactive than others, all right? So this is the idea. So where do we get these? All kinds of different places. So oxygen toxicity, radiology, toxic radiation. This is a type of injury that's damaging to the molecular structure. Inflammation does this, ischemia, lack of oxygen. And we get these activated oxygen species. So superoxide, we have an enzyme in our body to neutralize that called superoxide dismutase. Hydrogen peroxide, hydroxyl free radicals. So these can be very damaging, and they're called activated oxygen species, all right? And this video is fun. If you're just curious, it's talking about bonding. I kind of like this, but a lot of it is well beyond what we're talking about in this course, but it's kind of neat. Now, green chemistry. So I said you were going to keep building on these ideas of green chemistry. And the one that's talking about here is chemical bonding. And obviously for a lot of industry, right, we need to form these chemical bonds. And I had mentioned to you before that in order for a lot of these reactions to take place in an efficient way, we need some sort of catalyst. So with that, very often I had mentioned that these catalysts can be precious metals and or be very expensive and damaging to the environment to mine them. So the desire here is to develop other catalysts, biological catalysts or catalysts from that are more prevalent in the Earth's crust, so they're not as damaging, or things that can be recycled. The ability to use natural products, or not natural products, I mean to say biological products. And other ways of helping these different reactions to take place is giving them a platform to take place on, sort of a scaffold to facilitate the formation of the bond, all right? And another really important place where we're looking at chemical bonds is in terms of drug design and the desire to be efficient on that. So we're not wasting and putting out stuff we don't want into the environment. And that takes place with the other ones as well. So there's a little unit on this, and we watched this video in class talking about this bonding and the use of catalysts. And that's sort of what I wanted to focus on now. And again, we're going to keep building on this idea as we go through more and more of our chemistry. But in this case, we mentioned it here because we have this bonding, and we know that in order for these bonds to form, there has to be chemical reactions. So catalysts can help this take place. And the other thing is to provide platforms so that these reactions can take place more efficiently without needing as much of a solvent, all right? And I've already spoken to you about this. So this is a theme, and hopefully this is one that's becoming very familiar to you, okay? And then the other thing is when it comes to drug design, the desire is to form drugs that have a less toxic effect on the body, so that the reactions are very, very specific. So if you really understand the bonding and the bonding chemistry between them, you can have fewer side effects and much more specific reactions, all right? And also an increased potency to the effect, all right? And I think that's everything that I was sort of wanting you to get out of this chapter 4. And hopefully you're finding that as we go forward in the course, even now you're starting to grow in your general understanding of how this chemistry is working, all right? And yeah, so that's it for this chapter. And again, remember, we're going to keep building on these subjects. So just a little bit of time, and hopefully by the end of the semester, you're going to feel much more confident than in a lot of these ideas than when you came in on the first day of class. Okay, all right, so thanks a lot, and I will make another video for the next chapter. All right.